Yeah, hello class. Are we fine? Yeah. Now we are back for the third topic, and we saw the first two topics, and the first topic was the chemistry and society. Then we saw the second topic as experimental chemistry. Is that right? Okay. Then today we are bringing in the third topic. We hope it will run for roughly 1 hour. Now, our third topic today is states of matter. States of matter. That is topic 3. States of matter. States of matter. Now, under the states of matter, we also have various subtopics, and the first subtopic is we shall look at meaning of matter. Meaning of matter. Meaning of matter. Then too, we shall look at the states of matter themselves. States of matter. States of matter. 3. We shall visit what we call particulate nature of matter. Particle form of matter, or we call it particulate nature of matter. Particulate nature of matter. That one we just mean the particle form of matter. Particle form, another word. Now, the fourth one, we shall have to visit the kinetic theory of matter. Kinetic theory of matter. Kinetic theory of matter. Then the fifth subtopic here, the fifth subtopic will be after kinetic theory of matter, shall look at characteristics of various states of matter. Characteristics of various states. Various states of matter. Various states of matter. So then, after looking at the various states, we shall also provide evidence for subtopic 3. Evidence or proof for the particle form of matter. That's evidence for particle existence. Particle existence in matter. Do particles really occur in matter, or it is a thought? We shall prove that. Then next, we shall look at now change in the states of matter. Change in states of matter. States of matter. That the state can change from one form to another. FGH. The H subtopic there would take us to heating and cooling curves, which is the last. Heating and cooling curves. Now, when we visit that will be the end of the states of matter. And within a session of like 1 hour we should be through. Now let us speak on the first subtopic called the meaning of matter. Meaning of matter. Meaning of matter. If we talk about matter, what do we mean? Now let us go to that. Meaning of matter. Meaning of matter. Now to view this, to understand this, I would refer you back to our first topic, where we saw the first topic was chemistry and society. We looked at some common materials around us, and you mentioned some of them, if you remember that first lesson. And some of the materials you mentioned, I would like you to remind me, because now I want to know what's really matter, in reference to our first topic where you mentioned some of the materials that were around us. Can somebody remind us of some materials that are found around us, where we stay, where we live, anywhere? Yes, let us have patience reminding us.
Tables, chairs, pencils.
We have tables. Says we have tables. Again, chairs, pencils, pens, chemicals, water. There are so many, not so? Yes. Now, who recalls what did we say the chemical, the scientific word would be called? What did we say they were? After referring them to being materials, we said they were? Yes, somebody there, this is Aspolo. Aspolo, what did we say those materials were? Matter. We said they were matter. We said those materials were matter. Indeed, they are matter. Yes, that's right. That's right. Now, could somebody pick out the meaning of matter in form of a definition now? What is matter? What is matter? If this is matter, and then what's matter? Let's have Yuko helping us there.
Matter is anything that occupies space and has weight.
Matter is anything that occupies space and has weight. Could you explain further? Does a pencil occupy space and has weight? Sure. That means that qualifies this to be matter. Thank you very much. That means matter to us by definition means anything that would occupy space and has weight, or rather mass, not so? Can say weight or mass. Thank you very much. Now, that's very, very good. Does it mean that everything on earth is matter? Does it mean so? Somebody's nodding the head saying no. Oh, that means everything isn't matter. But all that we see with the eyes, does it mean matter? No. Because you would say light is not matter, not so? That's energy. That because matter and another aspect on earth is energy. Anything other than matter and the energy, if something is not energy, then everything is matter. Of course, that's what we picked from physics the other time. We would mean that on earth we have either matter or energy. Not so?
If an item is not energy, then it's matter. Surely. Thank you very much. That means we've visited that meaning of matter as the what? You said it is anything that would have weight and occupy space. Not so? Now, states of matter. Subtopic 2. States of matter. Now, we would like to know how many states does matter have. Now, let me use what you've given me here under the materials we mentioned at first here. How could we categorize some of these materials? Table, chair, pencil, pens, chemicals, water. Could you identify some way of categorizing them in some form of groups? Yes, Aspolo. How do you categorize those different materials that you have listed?
The tables, chairs, pencils, pens, all these are solids.
Okay. The tables, the chairs, the pencils, and the pens are all solids. That's good. Correct.
Then we have water, which is a liquid.
Water is a liquid.
Yes.
See, now, are you saying that in categorizing materials, we would mean that you can have different forms as a solid, liquid? Only?
And we also have the gas.
The gas on earth here, that means some other forms of matter would be a gas, not so? Oh, now in brief, how many states does matter have, or how many states do materials exist in? So, how many forms do materials or matter exist in? Let us have patience. Yes? Matter exists in 3. Mention them, namely? Solid.
We have the solid state,
Liquid state.
liquid state,
Gaseous state.
gaseous state, or gas, not so?
Oh, that's pretty good. Thank you very much. That means matter is basically and commonly 3 states. Clear? 3 states. Now, but scientists have the 4th state of matter, which is called the plasma state. See, now that's uncommon to you from primary level, because you basically say you have solid, liquid, and gas, not so? But then we are seeing that plasma is also a state of matter. That sounds a bit very, very new to your head. Now, to call this at your attention, let me first pause on this form here, because it seems you are aware of this. Listen now. Now, the plasma state of matter is a form that is very, that scientists have really put in keen interest. It's the most important state to the technological advancements in science. Listen, the plasma state is the gaseous form of matter also. Plasma is a gas, but it has some small property different from a gas in that the particles that make up the plasma state are charged. That plasma state is kind of a gaseous form of matter with charged particles. See, that's a bit charged particles. Now listen. When a gas is subjected to a very high temperature, the particles in the gas get ionized. They get charged. And the charges that we know are positive and negative charges. When you expose a gas to a very high temperature, then it loses some, the particles in the gas lose some other very tiny particles from them called electrons. We shall see that later in the topic ahead called the elements. Now let me briefly close up this. Plasma state is a gaseous form of matter with charged particles consisting of positive and negative charges. It is very important to scientists, very important in transmission of radio waves. See? And it's near very hot places like the sun, because the sun is very hot and causes the gaseous molecules to get charged. Now that's the fourth state of matter. I hope now everything is clear. Thank you very much. Let us shift very fast to the particulate nature of matter. Particulate nature of matter. Now, that one will take us to particulate nature of matter as the third subtopic. Keeping time, particulate nature, particle form, particulate nature. When we say nature, we mean the form in which you find something in. Nature, form. Now, particulate nature of matter, when we say particulate nature, we mean that does matter have particles? And we want to see, indeed, is matter having particles? Matter is just a myth, a thought. See? And we shall prove this, that matter indeed has particles in it. Now listen. Now, scientists stated some theories, we call them scientific theories about matter. And those theories are under what we call particulate nature of matter. So, now, before I visit those theories by scientists, I would first look at this case here. Assuming we break a small piece of charcoal, you pound it into two, you form two pieces, both will be charcoal. And again, keep breaking and breaking and breaking. You will break until you won't see any more particle. It means you will break, the particles will become so tiny until they no longer exist. They will be existing invisibly. See? They will be existing invisibly. That's why when you look at a soil can break down into dust and into invisible particles. That would mean that matter, as you go to breaking it and breaking it into the tiniest particle, the tiniest particle of matter would not be seen. See? That's correct. It wouldn't be seen. Now, look here. Let me write some of the theories, the scientific theories that scientists gave about matter. Then we shall go into details here. Now, scientists gave theories. A theory, as we saw earlier, that a theory is just an idea explaining a fact. It explains some facts. Ideas explaining some facts are called theories. Now, scientists gave the first scientific theories on matter. The first scientific theory was that matter consists of tiny particles. That's point one. Listen, because we shall relate particle nature to kinetic theory, which would explain the characteristics of different states of matter. Therefore, you need to listen. Now they said, in speaking, they said that the first scientific theory was that matter has tiny particles. And they continue to say that those tiny particles have spaces in between them. Clear? Follow very well because it will help me ahead here. Next, they say the particles attract themselves. See? And you can't attract another if there is no force of attraction. So they say that particles attract each other. Point 1, matter has tiny particles. Point 2, there are spaces between the particles. Point 3, particles attract each other. Point 4, the particles are in a state of motion. That the particles keep moving in matter. Then point 5, that the speed of motion of those particles depended on temperature. When you increase temperature, the particles moved very, very fast. See, now those were the scientific theories to explain that matter has particles, which we shall prove ahead there. Now, turning here to let us engage in another theory here, specifically called the kinetic theory of matter, before we go ahead here. See, kinetic theory of matter. Kinetic theory of matter was picked as a summary of these scientific theories. Now it said that matter consists of very tiny particles. Matter has tiny particles which are in a state of random motion, and the speed of motion depends on the temperature. See? Now, those were a summary of the particulate nature scientific theories of matter. Now that one will now throw us here to what we call characteristics of various states of matter. Let us stand there. And in the discussion of the characteristics of various states of matter, I would request you to refer to our scientific theories here that you have stated, and in summary of the kinetic theory. Now that is our next subtopic called the characteristics of various states of matter. See, now we want to see how is a solid different from a liquid, different from a gas. Now we would speak less on the plasma state because its characteristics are a bit quite different from these other three forms of matter. Now, let me pause for you a discussion there. You try to look at the differences between a solid, between a stone and water and oxygen gas. Now, differences between that's a stone. Also look at water and oxygen gas. I would like you to discuss those differences in terms of density. In tabular form, you draw a table, you discuss out the stone, water, and oxygen in terms of density, volume occupied, shape of that substance, easy to flow
is to flow, or pour is to pour. Which one can you pour? Then compressible, compressibility. Is it compressible? See? Which one is strong? Strong.
Now, in 5 minutes, I will not give you a lot of time because we have little. In 5 minutes, can you discuss out these differences between a stone, water, and oxygen in terms of density, volume, shape, easy to pour? Does a stone, can you pour a stone? Or can a stone pour some part of itself off? Compressibility. Can you squeeze a stone into a smaller size? Strong. Take some 5 minutes, and somebody out there in the virtual classroom, if you are two with a friend, you can try out discussing some of these differences between a stone, water, oxygen in terms of the following properties that we have mentioned here. That's density, volume, shape, ease to pour, compressibility, strength.
Yes. In stone. The stone is the strongest.
Yeah, thank you. You have finished. Yeah, now we can discuss over that. One person can present those findings. Can we have one person who is ready to present over? Patience, present those findings.
Okay, we are discussing differences between stones, water, and oxygen. The difference in density is that a stone is the most dense. Then water is more dense and oxygen is the least dense. Then the difference in volume is that the volume of the stone is fixed, the volume of water is also fixed, and the volume of oxygen varies. Then in shape, a stone has an irregular shape, water has no shape, and oxygen has no shape. Ease to pour, a stone can't flow, water can flow, oxygen can also flow. Then in compressibility, a stone can't be compressible, water can't be compressible, but oxygen can be compressible. Then in strength, the stone is the strongest, water is stronger in strength, and oxygen is weak.
Okay, thank you, Patience, for the presentation. Now, in summary, you have said the stone is the most dense. That means very heavy. Water is dense. When we are using English, most dense, dense, least dense. Not so? Then maybe let's reach it here. Now for volume, a stone has a fixed volume. That's right. That means it occupies a fixed space, because volume is the space occupied. Then you say the water has a fixed volume. That's correct. Water has a fixed volume. That's correct. Then you said oxygen's volume varies. Okay? That means it has no volume in short. See? Then shape, you say the stone has the shape which is irregular. That's correct. The shape is irregular. To be irregular is to have a shape. That means the stone has a shape in simple terms, though irregular it is. Water has no shape. That would mean when you pour water in a round container, the shape is round. When you pour it in a rectangular container, the shape is rectangular. That means water takes on the shape of the container. Then a gas, which is oxygen, has no shape, thank you. Easy to flow, easy to pour or flow. A solid can't pour, but you can pour a liquid and pour a gas. That's correct. Compressibility. You said you can't compress a solid. What of a liquid? Can't be compressed.
Can you demonstrate that one?
That a liquid cannot be compressed, neither a solid, but a gas can. Now that one, I would request you to use this water bottle to demonstrate that indeed a liquid can't be compressed, but a gas can. In this water bottle, you'll fill it with water up to the brim, up to the top, up to the top, up to the top. Can use a beaker, one of you, use a beaker, Juko, fill to the brim, then after filling to the brim, you compress it, and also you empty it and compress it. Then we observe. Somebody out there in the virtual classroom, you can try out that. Fill to the brim, there is some space left. Pour carefully away from the book. Yeah. Tie tightly. Then try to squeeze it or compress it. Is it accepting to be compressed? No, it's not accepting to be compressed. Empty it and squeeze it emptied. And squeeze it empty. Yeah, that means the empty container which is containing air is compressible, not so? Yeah. Now, going to strength here, we say the solid is very strong, a liquid is not, and a gas is not. Now, thank you very much. Now we can indeed improve this table by changing a stone to solid, water to liquid, then decide to a gas. That means these factors would now be true, not so? A solid, the solid is very dense, a liquid is dense, a gas is very less dense. Then you say the volume, stone has a fixed volume, water has a fixed volume but no shape, fixed volume but has a shape also, no volume shape, not so? You have been very good class. Then you said a solid can't pour, a liquid can pour, a gas can pour. Then you say the compressibility. Now, we shall pause a bit here. Why is a solid compressible? Now we would do, let me clear off this part and we look into actually why those properties were so. What makes that possible? Now, from those properties we can see that a solid can't be compressed. To compress is to make your particles come together. Is that very, very right? To compress is for the particles in a substance to come together. Now a solid can't be compressed. Simply the particles in the solid have no space. No space. To be compressed, then a liquid
In a liquid, then in a gas, yeah.
Now, what made the solid resistant to compression is that its particles
Could not allow space between.
them. There was no space to extend to each other. But in a liquid there was some compressibility because there are spaces that you can extend the particles close, not so? No, liquids are incompressible. Of course, because there is very little space to allow compression to take what? Place. These are incompressible. Then for a gas it's compressible because there is enough space. That's very, very right. Now, let me close this session of the properties by asking a question. Why do you think solids are very strong in reference to our scientific theories that matter has tiny particles? There are spaces between particles. The particles attract themselves. See? The particles are in a state of motion. See? And the speed of motion depends on the temperature. Now, why do you think solids are strong? Could somebody think very deep there? Why is a stone very hard and strong? See? Let us have us for discussing that part there.
I think the stone is very hard and strong because being that the stone is a solid, it does its particles closely packed to each other. And this makes, these particles are strongly packed to each other by forces called intermolecular forces. And these forces make the stone to be strong.
Thank you very much. Why the stone is strong is the existence of forces between the particles. Now he brought in another term called intermolecular or interparticle. Now molecular we shall look at it ahead there. That the existence of strong attractive forces makes the stone very strong. Now let us close that session, shifting very fast to what can prove that indeed there are particles in solids, gases and liquids. Evidence for existence
of particles in solids and gases.
Is it a thought that matter has particles? Or scientists keep guessing? They don't guess. Now, scientists proved that indeed those different states of matter had particles. How did they do that? They did it by some two processes here. The first one was called diffusion. Then the next one was called Brownian motion. These were proving that indeed there are particles in matter, or it was a simple proof for the kinetic theory of matter. That means the same question can be, what is the proof for the kinetic theory of matter? These are three proofs. Brownian what? Motion. Now, let me pick on the first one. They are called Brownian motion. In the early centuries, when science was at its younger stage, when science was young, some scientists like Robert Brown were looking at matter in depth. To explain to you Brownian motion, I would simply refer you to a simple experiment at home. When you wake up in the morning and the sun has shone through a ventilator, there is a ray of light from the sun through a ventilator. If you look at that ray of light in a dark room in the morning, what do you see? Let me repeat. We are trying to show you what Brownian motion means and how it proves that matter has particles. Now, wake up in the morning at around 7 when you have not switched on the lights. Observe a ray of light from the sun and look through that ray in the room. What do you notice? Who has ever seen that? Yes, you have ever seen that at home? Yes. What did you see in that bright ray of light from the sun? You saw some particles moving randomly. What particles were those? From where? Did you try to find out where the particles came from that were moving randomly? They were in the kitchen. They were from the kitchen. Who else saw? Who has ever seen those particles in a room? Or when you flash a torch through a dark room, what do you see? You will see some meandering particles, not so. Where are they from? And why are they moving randomly? That was the Brownian motion experiment, but it was not done using that. That's simple illustration. Now, in the room, what you saw was dust. See? And dust particles were moving randomly from place to place. Now, why were dust particles moving randomly from place to place? Do you have an explanation? Yes, Yuko, you seem to have an idea again. Yes. Why were dust particles moving randomly?
I think I heard this idea from the speed of motion depends on the temperature. So because of the heat from the sun, if the heat from the sun, make it more investigate and everything and make it very different.
Okay. The heat from the sun energizes the dust particles to move randomly. That's very good. Now, let us try to see it in depth. Now, you see in a room there, in that room, there is air. Not so. There is air because we shall see ahead there that air is just the atmosphere around us. See? Now, that air was mixed with dust particles. Now, air is invisible. And indeed, we know that that air has particles because you said every matter has particles, not so? See? Clear? Every matter has particles. See? That means the air in the room has particles. Now, when dust comes in the room, air is also moving randomly, particles are moving randomly, and also dust particles are moving randomly. Now they will keep knocking each other. The invisible air particles knock or collide with the visible dusty particles. And as they knock each other, they bounce from place to place. That's Brownian motion. Now,
Invisible air particles or particles that can't be seen in any matter are called atoms. See? Matter is built up from the smallest, tiny, invisible, unseen particles called atoms. See? Now, Brownian motion, we have seen that it's now the random motion of particles as a result of those particles colliding with the particles of the medium in which it has been placed. See? Now, who can, from that explanation that dust particles are colliding with air molecules or air particles, then how could you say that air has particles? What evidence could you draw from that Brownian motion to prove that indeed there is particles in air? Anybody who has picked something from Brownian motion to prove that a gas has particles? Of course, we are on the evidence. We want to know, is it really that a gas has particles, or we just assume that there is air around us? What can prove that? We have seen that the dust is moving randomly. See? Could you have any of that? For instance, could you explain that? How is Brownian motion giving proof to show that gas has particles? You can try. Patience.
When that beam of light passes through that dark room, and we see those moving particles, it's not that they are just moving out of the room.
Say it again.
It's not that they are just moving, nothing is causing them to move. I think it is because in a room it cannot just be crystal clear that there is nothing that is going to cause those particles to move. Either they can collide with the dust particles in the room, causing movement, either they can be moved by wind, and that beam of light, I think it enables us to see those particles.
Thank you very much, Patience. That in simple terms, the moving dust particles are not colliding, are not just moving randomly from space. It's that the invisible particle, when it's moving, it will meet, because it would move anywhere, any direction. By so moving, it knocks another particle and it changes direction. These are air particles in the room which are not seen, but these are dust particles which are seen. See? Okay, thank you very much. That now air has particles because it is causing other particles to move randomly. Now Brownian motion was demonstrated in a gas and in a liquid. But in brief, in a gas, we have demonstrated it by air and dust. In a liquid, it was demonstrated by using pollen grains which were dropped in water. When pollen grains were put in water and observed under a microscope, pollen grains were seen moving randomly. Could somebody pose some explanation there? Why did pollen grains in an experiment with water move randomly when observed by a microscope? Yes, yeah, we have another Asipolo.
The pollen grains moved randomly because being that they were poured in water, there was collision between those pollen grains and the water molecules, and so it makes them move to and from in any direction. It's causing the random motion.
Thank you. Does it prove that water, which is a liquid, has molecules or particles?
Yes.
Indeed, it proves so. Now that's the first evidence for existence of particles. Next evidence is diffusion here. What is this process that we are calling diffusion? Diffusion. Now, diffusion. We would refer to a simple experiment here of two gases. But before referring to the two experiments here, I would ask you a question, especially this would go to girls. Patience, when you use a perfume in your bedroom, I don't know whether you use a perfume or you don't. When you use a perfume in your bedroom, your brother will smell a perfume in his bedroom, near your bedroom. Why do you think the perfume was smelled by your brother? The perfume diffused. Or in simple terms, the perfume moved from your room to the other's room. Oh, that would mean movement of a gas from one place to another is what we are calling diffusion. See? That means you can't smell the perfume unless the perfume was actually matter. Not so? Does diffusion prove that there are really particles in nature? Let us say it again. Diffusion would mean the movement of a gas from one place to another. That is layman's explanation. But in simple terms, scientifically, it is the spreading of particles from a region of high concentration to a region of low concentration, where the perfume is being sprayed from to where there is no perfume at all. How would that perfume prove that indeed there is particles in a gas? And in this case, the gaseous particles are the perfume particles. Could that give evidence to you? Does smelling a perfume in your room prove to you that there is particles in matter? Who can relate that to the existence? How could you relate that diffusing perfume to existence of particles in matter? You want to have another person here? Okay. As Paul relate that, how do you relate the smelling perfume from one room to another as a proof that matter has particles?
From what I think is that being that air is made up of molecules or particles. Now when the person gets the perfume and sprays it maybe on her body, the particles of air in that region have the high concentration of the perfume. And being that now this concentration of the perfume will be moved from one particle of air to the other until the person in the other room also smells the perfume.
Okay. That would prove that indeed there is particles. See. Thank you very much. Now, that's a simple proof for diffusion, but in the laboratory we can go ahead to prove diffusion from a crystal of potassium permanganate. We have seen diffusion can occur in liquids and gases, because particles in a liquid can move as well as particles in a gas can move. And the diffusion can't occur in a solid simply because the particles do not move. Not so? Then if particles in a solid don't move, what happens to particles in a solid? What happens to particles in a solid? That's Paul. If they don't move, then what do? They
vibrate.
Exactly. Particles in a solid simply vibrate about their mini positions, about some area in which they exist. They vibrate in that area. We call it the mini area or mini position. Now, we can demonstrate diffusion. We have seen diffusion in gases, like we saw Brownian motion in gases and liquids, not so? Brownian motion in gases, we saw dust in air.
In liquids we saw pollen grains, in water. Diffusion in gases, we have seen perfume being sprayed and moved from one room to another. But that one we can do it also in the laboratory using two gases to prove that indeed they are diffusing. We can just demonstrate that using two gases, ammonia gas and hydrogen chloride gas. Send me two because we want to show diffusion in gases again using ammonia gas and hydrogen chloride. Now, ammonia gas, we are going to get ammonia gas from ammonia solution. From ammonia solution here. When I pour a little of ammonia solution, a little of ammonia solution, a little of ammonia solution which is concentrated. Ammonia solution produces ammonia gas. Then I pour a little of hydrochloric acid which is concentrated here. Concentrated hydrochloric acid gives off the gas called the hydrogen chloride gas, which are mist fumes or white fumes, mist. Now we are seeing those mist fumes. We are seeing those mist fumes. This hydrogen chloride gas that is spreading out. When I bring it near ammonia, ammonia gas would move towards hydrogen chloride gas, and you'll see something being formed. We can see that the two gases, there is something that we are seeing, very dense clouds there. The colorless gas from here has entered this hydrogen chloride section, and there are dense white fumes. But because of the effects of this, we shall not proceed further. Yeah, now that the formation of a new substance there from ammonia gas and hydrogen chloride gas due to diffusion has led to that. Now, that's diffusion in gases. But we can do that in liquids using a crystal of potassium permanganate, which we can place at the bottom of, can place it at the bottom of a beaker and observe it for some time. When we put a crystal of potassium permanganate at the bottom in colorless water, this is water, potassium permanganate crystal. When we do it practically, potassium permanganate crystal would make the water look purple. When we place it at the corner here and leave it for some time, it will spread through the water, and the water will definitely turn into purple. This one we can try it in the laboratory, but due to Due to time, we can just demonstrate here very fast how the water will appear when we add a crystal of potassium permanganate. When we add a crystal of potassium permanganate, as we try to wait for the experiment, when we add it down there, it will spread through the water. The particles on this crystal will leave the potassium, will leave the crystal section and keep spreading until the crystal is normal, showing that the particles of potassium permanganate have spread throughout the whole water. That would make the water turn into purple. The water turn into purple after some time. That would demonstrate to us diffusion in the liquid, which would be an evidence, which would be an evidence for diffusion in liquids, a proof for the particle existence in matter. Now, as I'm going to show the appearance of that water after some time, now we'll demonstrate it roughly very fast here. Just adding water to this potassium permanganate crystal, the water would turn purple after some time. Now the ideal experiment would be, we would get a glass tube and carefully put a particle there, then let in the particle at the bottom carefully. Then the color would spread and the water would turn purple after some time, as you have seen. Now the spreading of the particles of potassium permanganate in water would definitely prove to us that there are particles in matter. Now, because of time, to save much time and finish the other subtopics, let us turn very fast to the remaining two subtopics. The first one is the other subtopic was change in the states of matter. Change in the states of matter. Now, under change in the states of matter, I will request you to, in 5 minutes, to discuss the conditions and the different states of matter which are observed when ice is heated. Which are observed when ice is heated. When ice is heated, what are the different changes that we would observe? Could we discuss that? When ice is heated, what are the different changes that would occur? When ice is heated. Let's say ice is heated until you reach 100 degrees C. What would be the various changes that would occur to ice when heated? Okay, have you found out? Yes, one of you present to us. Yes, Patience, what are the different changes that would occur to ice there?
If the ice is heated to 100 degrees Celsius, before it reaches 100 degrees Celsius, it will have to melt to water. Then, when it reaches to 100 degrees Celsius, then it will turn to vapor.
To vapor.
Yes.
That is steam, vapor. Thank you very, very much.
Now that when ice is heated, the students have said that it would definitely change from ice form to the water form or liquid form and finally steam. Is that very, very correct? Now, ice is a solid. Agreed?
Yes.
Water, this part is a liquid, clear. Then steam is a what? A vapor.
Now, these are the different changes that have taken place when you subjected the ice to heating, not so? Now, let's look at the other way around. If steam is condensed until we condense it to 0 degrees, this would be the reverse, not so? Steam would turn to a liquid, liquid goes to ice. So that's right. Now, how do we call these processes that have taken place? If we are moving from ice to water, what has actually taken place? Melting has taken place. Melting. Okay. Water to steam.
Evaporation. Or we call it boiling. Evaporation. What is the reverse here? Steam to water.
Condensation.
That's condensation. Steam has condensed. Condensation. Then water to ice.
Freezing.
Freezing. Clear? Freezing. Freezing. See, that freezing is the change from a liquid to a solid. Clear? Assuming there was, can a certain change be that? From solid direct to vapor? That will be sublimation. Sublimation. That would be sublimation. Now, let us try to look at it in depth here. In terms of energy, heat energy, to change from solid to liquid, is it putting in energy or losing energy? Putting in energy. Heat is required, not so? What does the energy do to change the solid to a liquid? What does the energy do? What actually takes place during solid to liquid, which is melting? Yes, Patience.
I think the heating that is taking place breaks down the intermolecular forces.
Breaks down those forces in the molecules.
Yes, in the solid, and which breaks, when it breaks them down, it means the solid is going to become weaker. And during that process, the solid can easily melt. But not all solids.
Can now easily melt. Oh, the heat energy is to break down the forces so that the particles are set free to move.
Yes.
Clear. Because in liquids, particles move a bit freely than in solids. Okay. That means change from solid to liquid is application of heat energy. Energy is absorbed, energy is absorbed. But the reverse process means that you must do what? If you are coming from vapor to a liquid, then it's called condensation. That means, what does it mean in terms of energy? Energy is lost or gained. So, Aspolo, what happened? Energy is lost. Why do you think the vapor changes to a liquid on losing energy? What actually takes place when energy is lost? So, yeah, what actually takes place? Yes, takes place there. Because we are picking it from the kinetic theory. Yes, Juko, what actually takes place there?
The steam, what makes the steam to, what happens when the steam loses energy is, the energy is heat, and this steam is contained in heat. Now, when this steam loses the heat, which is making its fractions to be in kinetic energy, meaning when it loses the heat, the particle will not have any kinetic energy, they will not have motion, so they will come to rest. All the motion reduces and the particle is all breaking everything up.
Oh, thank you very much. That when energy is lost, then there is a reduction in speed. So particles come to rest and settle close to each other. Thank you very much. Now we have finished up with changing the states of matter. Let us look at heating and cooling curves. Heating and cooling curves. Now, these different changes here, we have discussed them in terms of energy, in terms of processes. Then we want to see, but before we look at heating and cooling curves, could we give one substance which undergoes sublimation? Yes. What substance undergoes sublimation? One example. Yes, Aspolo. Iodine undergoes sublimation. Somebody has another substance? Yes. You have another? Yes. Iron 3 chloride. Iron 3 chloride and ammonia chloride. Thank you very, very much. Now, we would demonstrate sublimation using ammonium chloride here. But I think we can hold this to demonstrate it ahead of time there in another section of the chapter called the elements and the mixtures. We shall demonstrate this. Now let us go to heating and cooling curves here. Now when we are looking at these processes, the changes can be observed graphically. The changes can be observed graphically. Now a heating and a cooling curve is just a graph we get by plotting a curve obtained by plotting temperature against time. Temperature against time. Now before you look at a real experimental curve, we can look at a figure of this curve to just explain graphically some of these changes here. If we heat ice, now ice which is not melting is at a temperature below 0 degrees. Ice which is not melting is at a temperature below 0 degrees. See? Now, when we look at a graph of temperature against time, to explain some of these changes that occur to ice.
minutes. Now look here. When I have solid ice here in a container, it's not at 0. It's below 0 degrees. Below 0 would mean it can be negative 5, negative 10, depending on the cooling temperature. Now ice at, let's say ice was at negative 20 degrees Celsius. Then you heated it. See, you heated it. When you heat ice, listen, you are inputting heat energy. Clear? Simply you are increasing the temperature. That means temperature moves from negatives going positives. Now melting will occur at 0. When you heat ice, it does not melt there and then, not so. It first takes in the heat. The heat breaks all the forces, then it melts. That means during heating, there is a gradual increase in the temperature, because that temperature is input to break the forces in the solid particles, so that the molecules, the particles, are set free to move. Now at 0, ice starts to melt. Clear? During melting, all the forces have been broken. That means the melting stage does not involve more absorption of what? Heat. Since all the forces have been, the molecules just start spreading for quite some time. That means if this was 1, 2, 3, 4, 5, 6, 7 minutes. That would mean when you apply heat, heat is used to break the forces in the solid. Until 0, when all the forces have been broken, ice will take some time to change into the hollow liquid. Now, the time it is taking, the temperature is remaining constant here, because all the forces have been broken. The heat being applied is no longer being absorbed there, so there is no temperature increase. Then when the ice has melted and you have only the liquid, the heat you are applying now starts to break the forces in the liquid. See, forces in the liquid. When the forces in the liquid have been broken, then if all the forces have been broken in the liquid, further absorption of heat does not increase any temperature, because all the forces have been broken. Simply the molecule starts spreading and spreading in more space, called now a gas. That process now being called evaporation. And finally we end there. Now let us close down this subtopic by this. When you heat a solid, temperature increases until all the forces have been broken. Then the solid starts to melt. Some time occurs as melting takes place, because no more temperature increase, because all the forces in the solid have been set free. Molecules are just spreading. That's right. Then when the whole ice has melted, see what happens here is that the more heat being put is to now break the forces in the liquid. When the forces have been broken here, the forces are being broken here as you absorb in more heat. When all the forces have been broken at 100, there is boiling here. Boiling occurs for some time, no more heat
no more temperature increase because no more heat being absorbed, since all the forces have been broken. Then if the whole of the water has turned into steam, when you increase temperature, you are increasing temperature of the steam. Now, I want to pose questions. Which state of matter is found along AB? Which state of matter is found along AB? Yes, Juko? Solid state. Which state of matter is found along CD? CD. Yes, Aspolo? Liquid state. Which state of matter is found along DE? Liquid state. What's found here? Liquid. What's found here? What's found here? Gas. So, now, why does this remain constant? Why does the temperature remain constant along BC? Yes, Aspolo?
Because when it reaches 0 degrees Celsius, that is the melting point where now the ice will start to transform to the liquid. So during that point there, it will first take some time before changing the head from the solid to the liquid.
To liquid.
Yeah.
Because there is the heat being supplied is not to increase temperature again, but the heat, because the heat has now separated, has broken the forces, and now the molecules are just spreading freely. Always when there is change from one state to another, temperature has to remain constant. Now that's a heating curve. A cooling curve would be just the reverse of this, and the changes would be now from steam going back to ice until you reach the negative direction. Now, in summary, we are closing with the effect of cooling, effect of evaporation, which results into cooling. That would be the end, that cooling due to evaporation. And we can demonstrate this by asking you to pour some little methanol on your hands and feel. If you pour some methanol on your hands, how do you feel? You feel a fresh, cool breeze, not so? You can pour some methanol on your hand and feel that pour a little on your hand, since it will not stay there. Also put yours and they pour some little. You can rub on the hands. How do you feel? You feel cool. Why do you feel cool? Is there more methanol on that hand? Check, is it still there? It's no longer there. Why? It has evaporated. Why do hands feel cool? Yes, Patience.
I think because our bodies are warm.
Bodies are warm.
And the
Methanol
is
is cool.
cool. When we apply it on our hands, I think the heat from our bodies gives the ethanol heat and it evaporates.
Thank you. That simply when a liquid has evaporated, it has absorbed the heat from a surface and therefore leaving the surface with less heat. So we experience some cooling effect. Now that cooling effect is so important in maintaining our body temperatures. Thank you. That's the end of this lesson. You have been a very good class. We went through the meaning of matter. We went through states of matter. We also looked at particulate nature of matter. Do particles exist in matter? And we proved that. Then we saw changes in states of matter. Then we saw heating and cooling curves, and finally cooling that is due to evaporation that has taken place. Thank you for cooperation. Till the next lesson.